In this video, let's take a look at the simple permutation and combination formulas. While it is easy to plug in numbers to these formulas and obtain desired outcomes, it is more difficult to see how these formulas are derived. Understanding how these formulas come about provides a greater understanding of their use. On the top here, we have the permutation formula. If you'll recall, this formula is used when we want to know the number of rearrangements of a given number of choices out of a total number. For instance, how many ways can we choose two of these colors from this container here? Specifically, in this case, we are not concerned with choosing the same groups of colors. Otherwise stated, choosing red then blue is considered different than choosing blue then red. We treat each order as different even if the same items are chosen in a given group. By contrast, the bottom here shows the formula for the number of possible combinations of a given number of items if we choose out of the total number of items. This can also be understood as asking the question of how many different groups can be chosen. In this case, if we choose two colors out of the 6 items, how many different groups can we make from this? This means that the order in which we choose the colors does not matter, or that choosing red then blue is the same as choosing blue then red, so we would not count this as two separate groups. In combinations, the only concern is what the group actually consists of, and that each group is not the same as any other. So let's see this in action. If we were to have a container of 6 colors as shown here, how many permutations and combinations could we obtain if we choose 2 colors? And here shows the total number of rearrangements when choosing 2 colors out of the 6. As you can see, this results in essentially a 6x5 table, meaning that we have 6 times 5 or 30 permutations. This means that there are 30 ways to combine 2 colors if chosen out of 6, if we are allowed to rearrange the order in which the colors are chosen. Using this simple counting method is useful for visually seeing the number of different rearrangements or arrangements, but this can obviously become tedious and confusing if we want to choose even 3 out of 6 colors. So let's make some use of mathematics to make this process simpler. First is using the factorial. From a statistical standpoint, the factorial can be used to determine the number of different rearrangements, again indicating that order matters, of some number of items n. When all of these items are chosen and rearranged, the total number of different arrangements is equal to n factorial. And if you recall, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3, and so on. This is where the n factorial in the numerator of both the permutations and combinations formulas comes from. If we apply this to the problem at hand, we have 6 total choices, meaning n equals 6. If we evaluate 6 factorial, this gives us a total number of different rearrangements of all 6 colors equal to 720. Next, on the denominator, we have n minus r, where r is the number of items we are choosing from the total number of items we have, n. n minus r therefore means that we are subtracting the number of total items by the number of items we are choosing from that total. This of course leaves us with the number of items remaining after removing r items. In our case, removing 2 colors from a total of 6 leaves us with 4 colors remaining to rearrange. We then divide the total number of rearrangements given by n factorial by the number of rearrangements of the remaining items after choosing a given amount, indicated by n minus r factorial. This essentially divides out all rearrangements we are not concerned with, thus leaving us with the number of rearrangements we are interested in. In this case, 720 divided by 4 factorial becomes 720 divided by 24, which indeed simplifies to 30. This of course holds true for all situations like this, and not just when choosing 2 items out of 6. Now, let's bring our attention to the combinations formula. Here we have the same 6x5 grid as shown above, but you'll notice here that I have crossed out some of the groups. This is because, again, the number of combinations differs from permutations and simply means that the concern now is with the number of different groups, indicating that the order in which the items are chosen does not matter. For example, you'll see here that every duplicate group has been removed in the grid. This means that, for example, the red-blue group here is considered the same as the blue-red group here. Thus, one of these is crossed out since this is considered to be the exact same group. In the grid above, however, we count these as being two unique entities, whereas in the combinations, they are considered the same. If we were to go throughout this entire grid, we would see that the total of groups crossed out because there are duplicates is 15. Again, this can be done by simply counting, but this process would quickly become cumbersome. What we can do instead is realize that if we have a chosen number of colors R from the total, we can find out the total number of different rearrangements of R using factorial as we did above. If we take a look at what R factorial gives us in this case, this means that choosing 2 of the items equals 2 factorial, which of course is equal to 2 times 1, or simply 2. Now, since we are not concerned with these rearrangements, we have to divide by this number just as we do n minus r factorial. Again, we divide the total number of rearrangements, n factorial, by what we are not interested in, being n minus r factorial, or the number of arrangements of items remaining after choosing r items, and r factorial, the number of rearrangements of the items chosen. If we simplify, this equation becomes the same as the one above, except we have to also divide by 2. This means that we now have 720 divided by 24, then we divide this number by 2 in this case. Taking the above answer of 30 and dividing by 2 equals a total number of unique groups from 6 colors when we choose 2 equal to 15. If you look at this by counting, it can also be seen as 30 total groups in the grid minus the 15 duplicate groups that are crossed out, of course equals 15 unique groups or 15 combinations. Again, this holds true for all total number of items when choosing a number of items from the total and seeking the number of different or unique groups. The combinations formula, therefore, is the same as the permutations formula, with the added requirement that we must also divide by r factorial.